In this lecture, we begin Lecture 4 on Stability Analysis and Root Locus. The central question in control engineering is, will my system behave properly? A poorly designed controller can cause oscillations, saturation, or even physical damage. Stability is the most fundamental requirement. Today we study BIBO stability, which stands for Bounded Input, Bounded Output Stability. A system is BIBO stable if every bounded input produces a bounded output. Let us define BIBO stability formally. Consider a transfer function h of s equals n of s divided by d of s. The poles of the system are the roots of the denominator d of s. BIBO stability is determined entirely by the pole locations in the complex S-plane. If all poles have negative real parts, meaning they lie in the left half plane, the system is BIBO stable. If any pole has a positive real part, the system is unstable. Poles on the imaginary axis require special attention. The S-plane is divided into regions by the imaginary axis. The left half plane, where the real part of S is negative, is the stable region. Poles here produce responses that decay to zero over time. The right half plane, where the real part is positive, is the unstable region. Poles here produce responses that grow without bound. The imaginary axis, where the real part is zero, is the boundary. Simple poles on the imaginary axis produce marginally stable responses, constant oscillations that neither grow nor decay. The connection between poles and stability becomes clear through the impulse response. Each pole at S equals sigma plus j omega contributes a term proportional to e to the sigma t. When sigma is negative, the left half plane, the exponential decays to zero. The response dies out over time, confirming stability. When sigma is positive, the right half plane, the exponential grows without bound. The response diverges, confirming instability. When sigma equals zero, the imaginary axis, the exponential has constant magnitude. The response oscillates forever with fixed amplitude. Consider a first-order system with transfer function h of s equals 1 over s plus a. This system has a single pole at s equals negative a. If a is positive, the pole lies in the left half plane and the system is stable. The step response rises to a final value of 1 over a and stays there. If a is negative, the pole lies in the right half plane and the system is unstable. The step response grows exponentially without bound. If a equals 0, the pole is at the origin and the step response is a ramp, which is unbounded. So a simple pole at the origin makes the system unstable for a step input. For a second-order system, the transfer function is omega n squared over s squared plus 2 zeta omega ns plus omega n squared. The poles are at s equals negative zeta omega n plus or minus omega n times the square root of zeta squared minus 1. When zeta is between 0 and 1, the poles are complex conjugates in the left half plane. The system is stable with oscillatory decay. As zeta approaches 0, the poles move toward the imaginary axis and the oscillations become more persistent. When zeta is negative, the poles cross into the right half plane and the system becomes unstable. Let us compare three types of step responses. A stable system on the left shows a decaying oscillation that settles to a final value. This corresponds to poles in the left half plane. A marginally stable system in the center shows constant amplitude oscillation that never settles. This corresponds to simple poles on the imaginary axis. An unstable system on the right shows growing oscillations that diverge. This corresponds to poles in the right half plane. The stability of the response is entirely determined by the pole locations. There is an important distinction for poles on the imaginary axis. Simple poles on the imaginary axis produce bounded oscillations, so the system is marginally stable. However, repeated poles on the imaginary axis produce responses that grow over time. For example, a double pole at the origin gives a ramp response to a step input. A double pole at plus or minus j omega produces oscillations with linearly growing amplitude, t times sine of omega t. Therefore, repeated imaginary axis poles make the system BIBO unstable. Let us summarize the BIBO stability rules. All poles in the left half plane means the system is stable. Any pole in the right half plane means the system is unstable. Simple poles on the imaginary axis means marginally stable. Repeated poles on the imaginary axis means unstable. These rules apply to any LTI system described by a transfer function. In the next lesson, we will study the Routh-Hurwitz criterion, an algebraic method to check stability without computing the actual pole locations. This is especially useful for higher-order systems where root finding is difficult.